Hello class, welcome. For this week's lab, we will be doing a virtual lab. Experiment 22, the oxidation of iodide ions by hydrogen peroxide. For this lab, you will be required to determine the rate law for the reaction between iodide ions and hydrogen peroxide in an acidic environment. This will be done by observing how the rate of reaction is affected when a concentration of hydrogen peroxide, iodide ion, and H plus ions are changed. In addition, you will evaluate the effect of temperature and the effect of adding a catalyst on the rate of the reaction. Let's take some time to look at the theory behind this experiment. In a reaction, reactants are being used up to form products. As such, rate being a function of time, we relate this concept to time. That is, the rate of a reaction will be how fast the reactants are consumed or the products are being formed. In this reaction, 2 moles of a reactant A is combined with 1 mole of another reactant B, and together are being consumed to form a product P. The rate of a reaction can be expressed in either terms of reactants or products. As such, it could be expressed as a change in the concentration of an reactant A over the change in time. The stoichiometric amount of that reaction should be taken into consideration by multiplying it over the molar quantity, and by sign convention, since this is a reactant and reactants are consumed, then a negative sign is placed at the beginning of the expression. Similarly, the rate of the reaction could be expressed in terms of the reactant B or the product P. But in this time, because it is a product and products are being formed, not being used up, a positive sign is used instead. Another way the rate can be expressed is in terms of the rate law. This is, rate is equal to the specific rate constant K times the concentration of the reactants raised to their specific order of that reactant. Some points to be noted is that the rate law is expressed in terms of reactants, not products. And also, the order with respect to each reactant are not equivalent to the molar amounts of that reactant. This can only be determined by doing experiments such as this lab. For this experiment, you will be evaluating how the concentration, changes in the temperature, and the presence of a catalyst affect the rate of the chemical reaction. In this lab, 1 mole of hydrogen peroxide combines with 2 moles of iodide ions and also 2 moles of H plus species. These together are consumed to form 1 mole of iodine and 2 moles of water. The rate law for this reaction is therefore given as the specific rate constant K times the concentration of the hydrogen peroxide species raised to the order with respect to the hydrogen peroxide times the concentration of the iodide species raised to the order with respect to the iodide species, and also times the concentration of the H plus species raised to the order with respect to the H plus species. Remember, the order of the reactants is not equal to the molar quantities of that reactant. It is only determined by experiments such as this one, the initial rate method. When using this method, the experiment is usually carried out several times and the concentration of only one reactant species is allowed to change at a time. This is done so that when 2 runs or experiments are compared, the concentration of the reactants will be the same except for only one species, and thus this can be manipulated to find the order with respect to that species. Let's look at how this is done. In analyzing the data in the table given, we recognize that the concentration of reactant A changes while the concentration of the other reactant B remains the same for run 1 and 2. By dividing the rate law for run 1 by the rate law for run 2, or vice versa, this will allow some terms to be cancelled out. Concentration does not affect the specific rate constant, temperature does. But the temperature for this reaction is assumed to be the same, and as such the specific rate constant is not changed and will be cancelled out. Similarly, the concentration of reactant B and the order with respect to reactant B does not change and also will be cancelled out. By logging both sides of the equation, you can apply the mathematical rule that states that the log of any term raised to an index is the same as the value of that index multiplied by the log term. Making A the subject of the formula gives the order with respect to A as 1. In order to find the order with respect to reactant B, we do the same thing. Let's look at the data given to see which two runs only the concentration of B changes and perform similar calculations. For this, it is run 2 and 3. Now the order with respect to B is -1. Please note that the orders with respect to a reactant can be negative, and you will discuss the implication on the rate of reaction when this occurs in your lab write-up. This gives the rate law for this reaction as the specific rate constant times the concentration of reactant A raised to 1 times the concentration of reactant B raised to -1. In determining the rate of this reaction, an acetic acid acetate ion buffer is used to control the concentration of the H+ ion. A buffer is a solution that comprises of a weak acid and its conjugate base. It has the unique ability of resisting sharp changes to the pH upon addition of small quantities of acid or base. The acid dissociation constant for acetic acid is given at 25 degrees Celsius as 1.8 times 10 to the minus 5. For this experiment, you're required to find the concentration of the H+ species, and as such, you do this by making H+ the subject of the formula. There are various modifications that was done to the initial rate method for this experiment, such as the addition of thiosulfate and a starch indicator. When will thiosulfate be added, and why will it be done? Thiosulfate is to be added at the beginning of the reaction in the reaction flask with the other reactants. Since it does not react at an appreciable rate with any of the other reactants in this experiment, why is it being added then? Thiosulfate reacts rapidly with iodine, one of the products in this experiment, so that as soon as iodine is produced, it will be consumed in a side reaction with thiosulfate to reform iodide ions. This continues until all the thiosulfate that was added is consumed. Now, what does this have to do with the rate of the reaction? Remember, the rate of a reaction can be expressed in terms of reactants or products. Since the concentration of thiosulfate and the amount added is known, this information can be used to predict the amount of iodine that it reacts with. Thus, the rate of the reaction in terms of iodine produced can be monitored. Please note that reaction 3 and 6 are occurring simultaneously. So, If both reaction 3 and 6 are added, it shows a net reaction that relates the amount of thiosulfate consumed to the amount of hydrogen peroxide and H plus ions consumed over that period as well. Equation 7 does not show that hydrogen peroxide reacts with thiosulfate ions. No, it does not. Rather, it is simply being used to show that for every 2 moles of thiosulfate ions that reacts with iodine, 1 mole of peroxide and 2 moles of H plus ions are being consumed in the experiment as well. Why was starch added? The time taken for all the thiosulfate ions to be consumed is easily monitored and can be used to give information about the rate of consumption of the reactants in this experiment as we just saw. However, to monitor the time it takes for reaction 6 to occur, we need to know at what point it started and when it ends. We now know that it started at the beginning of the reaction as soon as iodine is produced. But at what point did it end? Remember, reaction 3 and reaction 6 are occurring simultaneously. When all the thiosulfate is used up, reaction 3 will still be occurring, so that the iodine produced, having no more thiosulfate to react with, will not be present in the flask and will form a blue precipitate or complex with starch indicating the end of reaction 6. Iodine and starch form a blue complex, and this intensity depends on the concentrations present. As we have been seeing, reaction 6 is directly dependent on reaction 3. The rate of reaction can therefore be expressed in terms of the consumption of thiosulfate with time. If this lab was done face-to-face, you would have been required to make up 6 reaction mixtures whose composition and temperature is shown in the table on the slide. To make up reaction mixture 1, you would be required to add the reactants in the order represented in the table except for hydrogen peroxide. First, at room temperature, you would have added 75 cm³ of water to a clinical flask, 30 cm³ of the buffer solution, 25 cm³ of potassium iodide, 5 cm³ of a 0.1% starch, 5 cm³ of sodium thiosulfate, and after which you allow this to equilibrate to room temperature and record the temperature using a thermometer. After recording the temperature, then you would have added 10 ml of hydrogen peroxide using a pipette. When half of the amount of the hydrogen peroxide is ran into the reaction mixture, you start the stopwatch, and at the first appearance of the blue coloration, you stop the stopwatch. The temperature is again recorded and noted. For reaction 2, 3, 4, and 6, the procedure is repeated and the temperature is taken. The clock is started when half of the stipulated amount of hydrogen peroxide is drained from a pipette as done before and stopped at the first appearance of a blue coloration, and the temperature recorded. This is not done in duplicate, so the only measurement that you would have taken in duplicate is mixture 1. For reaction mixture 5, the solution is prepared. As in mixture 1, the temperature is elevated, by placing the mixture in a larger beaker containing hot water and stir to the desired temperature, and the procedure carried out as before. You will be given individual data that requires you to calculate the orders of the reaction with respect to each reactant, that is, hydrogen peroxide, iodide ions, and your H plus ions, and also to evaluate the effect that the following have on the rate of the reaction: the increase in temperature and the addition of a catalyst. In calculating the orders of the reaction with respect to each of the reactants, let us first start with hydrogen peroxide. Let us look at the table of composition given to see in which two reaction mixtures the concentration of all the reactants remain the same except for hydrogen peroxide. We see that this is the case for reaction mixture 1 and 2. Remember, we had measured the time it took for the thiosulfate ion to be consumed and showed that since this reacted with iodine produced, this information could be used to relate to the rate of consumption of the other reactants over the same time period as well. Thus, the change in the concentration of hydrogen peroxide over time can be expressed in terms of the change in the concentration of the thiosulfate ion over the same time period times the reciprocal of its molar quantity. By dividing the expression for rate 1 by the expression for rate 2, or vice versa, the concentration of thiosulfate cancels out. Remember, when dividing by a fraction, multiply the dividend by the reciprocal of the divisor. The rate expression thus becomes rate 1 divided by rate 2 is equal to the change in the time for expression 2 divided by the change in the time for reaction 1. So let's go for that again. The rate expression becomes rate 1 divided by rate 2 is equal to the change in the time for reaction mixture 2 divided by the change in the time for reaction mixture 1. But remember that we can also express the rate of a reaction by its rate law. So if we divide the rate law for reaction mixture 1 by the rate law for reaction mixture 2, then the specific rate constant and all other terms relating to the other reactants also cancels out, so that the expression now becomes rate 1 over rate 2 equal to the concentration of hydrogen peroxide in reaction mixture 1 raised to its order divided by the concentration of hydrogen peroxide in reaction mixture 2 raised to its order. We also just proved that rate 1 over rate 2 is also equal to the change in the time for reaction mixture 2 to occur divided by the change in the time for the reaction mixture 1 to occur. So by logics, if A is equal to B and A is equal to C, then it's only logical that B is also equal to C. As such, the expression becomes the change in the concentration of hydrogen peroxide in reaction mixture 1 raised to its order divided by the change in the concentration of hydrogen peroxide in reaction mixture 2 raised to its order is equal to the change in the time for reaction mixture 2 to occur divided by the change in the time for reaction mixture 1 to occur. Also, because the volume of the hydrogen peroxide added in the reaction mixture directly impacts the concentration of the hydrogen peroxide in that mixture, we can substitute the volume for the concentration in this expression. By logging both sides and making A the subject of the formula, we can find the order with respect to hydrogen peroxide. Similar calculations would be done to find the order with respect to iodide ions using the reaction mixtures 1 and 3. We cannot just use the volume to find the order with respect to the hydrogen plus ions. This is because the concentration of the hydrogen plus ions are being contributed from both the buffer solution and the acetic acid added. So in order to find the order with respect to the H plus ions, we have to use equation 5 to find that concentration of the H plus ions. Use data also from reaction mixture 1 and 4, and remember to account for the acetic acid from both the buffer solution and the 0.3 molar solution. Calculate similar to what was done for hydrogen peroxide and iodide ions as before. To evaluate the effect of the increase in temperature on the rate of the reaction, use equation 1 and 5. The specific rate constant is affected by changes in temperature, and as such, the rate expression becomes as shown here. And similarly, to evaluate for the addition of a catalyst on the rate of the reaction, use mixtures 1 and 6. For additional information required to write up this worksheet, you'll be given individual data. Also, think about the safety and precautions that will be required for this lab had you done it face-to-face. Also, think about whatever assumptions were made during this lab. And your modified worksheet will be available to you on OVLE. Thank you for listening. Please do your individual readings and read over your procedure in your lab manual. Please bring all your questions and concerns to your lab session so that we may have a lively discussion. Goodbye.